So classification then is a way of categorizing data based on the predictions that we're going to create. Let's take a look, Steve, at how I might create a classification model using Azure Machine Learning.
Sure. So on my screen here, I've created a classification model for the PIMA diabetes example. And you've seen the first bit of this. You've seen importing the data and setting the column names and doing the join. So let's start from there. And as we did with the regression example, we need to do some data prep. And it's a little less this time, but one bit we have to do is we have these two columns, patient ID and physician, that are not in any way predictors of whether a patient is diabetic or not. They're just things that happen to have been assigned. So we clear those as features so we don't confound our model training. As we had with the regression example, we have some nonlinear behavior, basically some curviness in the relationships between the features and the label. So we're going to do just a little bit of feature engineering and take the log of age. And we do the two types of normalization, same as we did before. Z-score normalization for kind of normally distributed, bell-shaped curve distributed data, or min-max normalization for a fair number of our features that have some sort of odd distribution. Now, when we get down to the second half of my experiment here, this should look familiar because you just saw something not too different in the regression example, where we split the data, we train a model, we define which machine learning model we want to use and set its parameters. We score the model based on the trained model and the data we've held back, and we evaluate that model. So you've all seen that before. I'll just call your attention to the fact that in this case, we're using what's called a two-class logistic regression, which is a different model than linear regression. It is a two-class classifier model. All right, so let me run this for you, and we'll look at the result. All right, the model is finished running, and first we'll look at the scored model module output here. We'll just visualize that. And I'm going to scroll over. And you see I have my scored label, which can be 1 or 0. And I have my diabetic label, which was our original label. So we've got 1 and 1, 0 and 0, 0 and 0, 0 and 0, and 1 and 0. So we've got an error, and then 1 and 1, etc. All right. So it looks, reasonably good, but let's look at this more in aggregate with the evaluate model module. So first of all, we see this ROC curve that we discussed previously. And you see here's that diagonal line, which would just be random guessing. And if recall a perfect classifier, this curve would come straight up and go straight across. And it's somewhere in between. So it's a reasonably good classifier, but maybe not a perfect classifier. And we have the metrics we talked about. So here, those 4 numbers are our confusion matrix. So we've gotten a fair number of true positives correct, a fair number of true negatives correct. However, we have a number of false positives, 628 of them. Those are diabetic patients that we misclassified as not being diabetic, and we have a fair number of false alarms. We have 338 of what we call false positives, where we said they're diabetic, but in fact they're not. Our overall accuracy is a reasonable 78 or 79%, not outstanding. Our precision is 0.72 roughly. So that means we're getting the 72% of the cases we identify as positive actually are. But our real problem here is recall. So notice the recall is quite low. It's 0.58 or 0.59. So that means that we're missing about 40% or 42% almost of the diabetic patients, that we're not correctly capturing them. So that could be a problem. And what we might want to do in a case like that is we have this threshold, and we might want to start moving that over, and you see how it changes the number. So accuracy doesn't change that much, but recall goes up, precision goes down, and I can go a little further and get it around, say 90-something% recall. So that means now that we're getting over 90% of the diabetic cases correctly classified, but we're doing it at the expense of quite a few false alarms. Almost half of the cases we would classify as positive are false positives. So if we're willing to bear that expense of retesting or doing additional tests on patients who aren't in fact diabetic, we may want to push the threshold to the left here. So I hope that gives you an overview of how to do classification in AML, but also reinforces that general recipe we followed for doing supervised machine learning.